Okay, let's walk through the slide. Empower your PC experience with PCIe Gen5 technology. Alright, let's quickly address this page. This is our standard legal disclaimer. In a sense, it states that the information provided is for informational purpose only, subject to change, and doesn't constitute a commitment from Silicon Motion. It also covers intellectual property rights and licensing. I won't read it word for word, but I'd like everyone to take about 10 seconds to quickly scan through the key points. 9, 10. Great. Let's move on. Okay, let's kick things off with a look at the timeline for PCIe Gen5 SSDs. As you can see on the slide, we're mapping out the next few years. In 2024, we're looking at samples for Gen5 8-channel SSDs, with mass production kicking in by 2025. Moving on to 25, we'll see samples of Gen5 4-channel TLC SSDs, followed by mass production in 2026. And finally, in 26, we're expecting samples of Gen5 4-channel QLC SSDs, with mass production ramping up in 27. This first wave is really setting the stage for the next generation of storage technology. Now, when we talk about next-gen SSDs, there are 4 key areas we need to focus on. First up is performance, because, let's face it, speed is king in the tech world. Next, we've got energy efficiency. It's not just about being fast, but being smart with power too. Then there's platform resilience. We need these SSD to be robust and reliable. And lastly, peripheral interfaces, because it's all about how these SSDs play with the rest of the system. These 4 areas are really shaping the future of SSD technology. Let's dive into what we're looking at in terms of performance for Gen5 SSDs. For sequential read, we're aiming to max out that PCIe Gen5 by 4 bandwidths. We're talking about speeds up to 15 gigabytes per second. That's blazing fast. But it's not just about sequential performance. We're also pushing the envelope on random read and write speeds, especially for things like gaming laptops, where every millisecond counts. To put it in perspective, we're expecting Gen5 by 4 to at least double the IOPS performance of Gen4. It's a big jump, but that's what progress looks like. So next page, how do we actually achieve these performance goals? It's not just one thing. It's a combination of factors. First, we need solid Gen5 PHY support. Then we've got to push the boundaries of flash memory bandwidth. The controller selection is crucial too. We need some serious processing power to handle these speeds. And let's not forget about firmware optimization. That's where we can really fine-tune the performance. It's like building a race car. Every component needs to be top-notch and working in perfect harmony. Now let's talk about choosing the right controller. It's a bit like picking the right brand for our SSD. We're comparing the Cortex R5 and R8 here. The Cortex R8 is really standing out with its support for symmetric multiprocessing, or so-called SMP. This allows for better load balancing, which is crucial for multi-core performance. It also features out-of-order execution, which is great for handling complex tasks more efficiently. When we look at benchmark like Drystone and CoreMark, the Cortex R8 is clearly the superior choice. It's showing about a 1.5 times improvement over the R5 in key metrics. In the world of high-performance SSDs, this kind of edge can make a real difference. Moving forward to the flash memory bandwidth, this is really crucial stuff. To hit that Gen 5 by 4 8-channel maximum performance, we need flash dies that can support bandwidth above 2400 megatransfers per second. That's a significant leap forward. Looking at market trends, we're seeing a clear path toward Gen 5 SSDs. We expect to see them start appearing in premium platform by late 2024. After that, we'll see a gradual rollout across different market segments. It's exciting to see how quickly the technology is advancing. Now, let's dive a little bit more into the exciting performance metrics of our cutting-edge PCIe Gen5 technology. We're not just pushing the envelope, we're redefining what's possible in storage performance. First, let's talk about raw speed. Our sequential transfer rates are nothing short of breathtaking. We're seeing read speeds that exceed 14.5 gigabytes per second. That's not a typo. And our write speeds, they are keeping pace at over 13 gigabytes per second. This level of performance opens up new possibilities for data-intensive applications, from real-time data analytics to high-resolution video editing. But speed is not just about moving large files. In the real world, many applications depend on how quickly we can perform many small operations. That's where our random read and write performance comes in. Based on our simulation data and drawing from our extensive experience in firmware optimization, we're approaching an astonishing 2.4 million IOPS. That's 2.4 million input and output operations per second. And here's the exciting part. We believe that there's still room for improvement. Our projections suggest we could push this even further, potentially reaching 2.5 million IOPS. This kind of performance can dramatically reduce latency in complex database operations, improve responsiveness in virtualized environments, and enhance our user experience in AI and machine learning applications. And let's look a little bit more at some concrete numbers from our performance simulations. Using Crystal Disk Mark with a queue depth of 32 and 8 thread on a 1 gigabyte dataset, we're seeing random read speed of nearly 2.4 million IOPS and random write speed of 2.4 million IOPS as well. These numbers represent a quantum leap in storage performance. What does this mean in practical terms? Imagine loading complex 3D models in real time with no lag, running multiple virtual machines with the responsiveness of bare metal systems, or processing vast dataset for AI training in a fraction of the time it takes today. That's the power of PCIe Gen5, and that's what we're bringing to the table. And this breakthrough in performance is not just about impressive numbers, it's about enabling the next generation of computing applications. We're opening doors to innovations that were previously constrained by storage speed limitations. It's an exciting time in the world of storage technology, and we're thrilling to be at the forefront of this revolution. But it's not all about raw speed. We need to talk about power efficiency too. PC OEMs are setting some pretty stringent requirements here. They want Gen 5 SSDs to consume no more than 10 watts under maximum performance. But it's not just about peak power. We also need to maintain performance as we scale down power. For example, at 80% power consumption, they are looking for at least 80% of peak performance. It's a tough balance to strike, but it's crucial for the next generation of mobile and power-conscious devices. So how do we meet these power requirements? Well, we are attacking the problem from multiple angles. First, of course, we're leveraging advanced process nodes to reduce overall power consumption. We're also focusing on low-power circuit design, especially in the fine layer. We're developing on intelligent power management controller, or PMC, to optimize power usage across different scenarios. And we're implementing smart thermal throttling to maintain performance even under challenging thermal conditions. It's a multifaceted approach to a complex problem. Let's dive a bit deeper into how we're using advanced process nodes. We've made the leap from a 12 nanometer process to a 6, and the results are significant. This performance alone has reduced power consumption by about 30%. To put that into perspective, our SM2508 controller can operate with power consumption as low as 3.5 watts. That's a massive improvement that allows for better performance within tight power envelopes. Now, let's talk about our PHY design. We've taken the approach of designing our PHY in-house rather than using third-party IPs, and it's paying off big time. Our custom designs are showing significantly lower power consumptions in both Gen 4 and Gen 5 PHY implementations. We're seeing power reductions of up to 20% compared to third-party solutions. This kind of efficiency gain at the PHY level transactions to better overall system performance and power management. Let's talk about power management, a critical aspect of modern SSD design. On this slide, you can see the traditional approach to power management in SSDs. Typically, the central CPU would manage all circuit modules, This includes the DRAM, the NAND flash controller, the PCIe interface, and other peripherals. While this approach works, it's not always the most efficient. The problem here is that the CPU needs to stay active to manage these components, even when the SSD isn't doing much. This constant activity can lead to unnecessary power consumption. In a world where every milliwatt counts, especially in mobile devices, we needed to think differently. And here's the new way. Let's look at our smart approach to power management. As you can see on this slide, we've introduced a game changer, the Intelligent Power Management Controller, or PMC. The PMC takes over the power domain control and management strategy execution from the main CPU. It's like having a dedicated energy manager for your SSD. This allows for more fine-grained and efficient power management. With this approach, the main CPU can enter lower power states more often, and is not constantly needed for power management tasks. The PMC can handle things like turning off unused components or adjusting power states based on workload, all without waking up the main CPU. The result? Significantly improved power efficiency without sacrificing performance. It's a win-win situation that's crucial for the next generation of high-performance, low-power SSDs. Now, let's shift gears and talk about thermal management. Another critical aspect of the SSD performance. We've developed an intelligent thermal throttling system that's a significant step up from traditional methods. Traditional thermal management often relies on simple frequency scaling. When things get hot, you just slow everything down, but this can lead to sharp drops in performance, which isn't ideal for maintaining a smooth user experience. Our approach is different. We've developed an intelligent system that allows for a more nuanced response to thermal challenges. Instead of just slowing down, we can make smart decisions about how to reduce power while maintaining as much performance as possible. This graph really illustrates the advantage of our intelligent thermal throttling approach. Take a look at the two lines here. The gray line represents traditional thermal throttling. See how it drops off sharply as power is reduced? That's the kind of performance cliff that users notice and complain about. Now look at the blue line. That's our intelligent thermal throttling in action. See how it's much closer to a straight line. This represents a near linear trade-off between power and performance. What does this mean in practice? As we reduce power to manage thermals, we see a proportional decrease in performance rather than those sharp drop-offs. If we need to run at 80% power, we can still deliver close to 80% performance. This meets the stringent requirements set by PC OEMs and ensure a more consistent user experience. even under challenging thermal conditions. Let's move on to another crucial aspect of modern SSD design: platform resilience. In today's interconnected world, security is more important than ever. We're implementing a comprehensive system where the host can verify the legitimacy of the entire SSDs. This isn't just about data encryption. It's about ensuring the integrity and authenticity of the entire storage subsystem. Our approach involves layered authentication, starting from trusted controller hardware. We're also incorporating a unique device secret for each SSD. This is like a fingerprint for each drive, ensuring that it can be uniquely identified and verified. These measures are crucial for preventing attacks and ensuring that the storage system can be trusted in security crucial applications. Now, on this slide, you can see a more detailed view of our advanced platform resilience approach. Let's break it down. At the heart of our system is DICE, the Device Identifier Composition Engine. This technology, developed by the Trusted Computing Group, provides a robust foundation for device identity and attestation. We start with a secure boot process, ensuring the integrity of our boot code. From there, we use technologies like GMIF and RSA to verify the integrity of the SSD firmware. This creates a chain of trust from the hardware all the way up to the running firmware. The really powerful part is how this extends to the whole system. Through a series of cryptographic handshakes and certificate exchanges, the host can verify the authenticity and integrity of the SSD. It's like having a secure handshake between the SSD and the whole system, ensuring that everything is above board. This comprehensive system authentication approach provides a level of security and trust that's crucial for modern computing environments, especially in areas like enterprise, financial services, and government applications. Next one, let's talk about how our SSD interact with the rest of the system. We're seeing a trend toward enhanced collaboration between SSDs and host systems. This goes beyond simple read and write operations. As you can see on this slide, we're implementing various protocols across different interfaces to support this enhanced collaboration. We've got thermal monitoring, attestation, recovery, and even debug capabilities, all running through these interfaces. This level of integration allows for more intelligent and efficient operation for the entire system. It's not just about storage anymore. It's about being an active, communicative part of the entire computing ecosystem. All right, let's dive a bit deeper into how we're supporting the enhanced communication. On this slide, you can see a layered approach to our communication protocols. At the physical layer, we're supporting PCIe I2C, SM bus, and I3C. This provides the foundational hardware connections. Moving up to the transport layer, we've implemented MCTP, or so-called Management Component Transport Protocol. This allows for flexible and extensible communication between different components. At the top, we have the protocol layer. Here, we're supporting NVMe and MI for management interface operations, and SPDM CMA for security and certificate management. This multi-layered, multi-path approach gives OEMs the flexibility they need to implement advanced management and security features. Now you see how it goes. You might be wondering, what does all this mean in practice? This slide breaks it down for you. Our Gen 5 controller supports a wide range of standards. We've got SM Bus Spec 3.1, NVMe MI Spec 1.2, and ICCC Spec 1.1.1. But it's not just about ticking boxes on a spec sheet. We've implemented practical features like address resolution protocol support, which helps with dynamic addressing. We've got alert support for real-time notifications, and we're supporting vital product data, which is crucial for system management and inventory control. All of these features come together to create a controller that's not just fast, but also incredibly smart and adaptable. Let's get into some of the nitty-gritty details. Our Gen 5 controller isn't just meeting the bare minimum requirements, we're going above and beyond. For example, our I3C operation frequency can go up to 12.5 MHz, allowing for high-speed communication when needed. We've also focused on power efficiency with a low power resume time of less than 5 microseconds. We're supporting MCTP over both SM Bus and I3C, giving OEMs flexibility in how they implement system management. And for security, we've got SPDM support also over both SM Bus and I3C. These capabilities allow for a level of integration and intelligent operation that simply wasn't possible with previous generation of SSDs. We're taking a flexible approach to peripheral interfaces. Traditionally, these interfaces were implemented with pure hardware circuits. But in our Gen 5 SSD, we're introducing an ARM M0 CPU for dedicated control. This allows for code upgrades, making our interface subsystem much more adaptable. It's like having a mini computer dedicated to managing how your SSD talks to the rest of the system, and it can learn new languages as needed. Okay, let's put it all together and look at what we've achieved with our first Gen 5 client SSD controller. We're talking about ultimate performance here. 15 gigabytes per second sequential read and 2.5 million IOPS for random read and write operations. But it's not just about speed. We've also achieved ultra-low power consumption with a maximum of 3.5 watts active power and as low as 2.5 milliwatts in sleep mode. We built in flexible peripheral interfaces and comprehensive platform resilience. And thanks to our upgradable design, this controller is future-proof. It's a powerhouse that's ready for the next generation of computing.
Sure.
To conclude it and to wrap things up, let's look at the bigger picture. We're seeing a relentless pursuit of performance in consumer applications, and our Gen 5 SSD technology is at the forefront of this. At the same time, PC OEMs are setting increasingly stringent power requirements, challenging us to do more with less power. We're also enabling enhanced collaboration between SSDs and host systems, going for beyond simple read and write operations. The exciting news is that we expect to see high-performance laptops featuring our SM2508 controller and PCIe Gen5 SSDs hitting the market by the first half of 2025. It's an exciting time in the world of storage technology, and we're thrilled to be leading this change. Thank you all for your attention.